Hello. Let's take a look at this model for designing science lessons, moving from the bottom to the top. Because effective science instruction is built intentionally. At the foundation of our teaching are the state standards. And I always tell teacher candidates that standards are not just compliance documents. They are descriptions of the kinds of thinking, reasoning, and disciplinary practices students should experience. So at this level, we're really answering the question, what should students know and be able to do? We started exploring this back in session 1. Then we move into lesson learning goals. These goals translate standards into student-facing learning outcomes. Now, this is a skill that we need to establish because the standards are the bigger ideas and the lesson learning goals are mapped to get to those big ideas. And this is where teachers begin making the instructional decisions. What exactly am I trying to help students figure out, right, in this phenomenon, in this topic? And what evidence would show me students are actually developing understanding, right? We worked that out in session 2. Now, let me pause for a second as a teacher educator. As I'm having this conversation with you and we're talking about planning, what instructional moves am I making as a teacher? And this is where I will pause and get information back from the group. Why do you think I started with the standards and the goals before activities? Why did I just start with activities? And you would pause and take some information from it. And then you land it, right? You say exactly, because they're going to tell you that we got to deal with um, where we're trying to get students to go intellectually and how we can tie their intellectual experiences, the accurate ones, to what we want the habits of mind to be in science. Because rigorous teaching is not just about engaging activities. It's about aligning experiences, thinking, and evidence of learning towards a coherent intellectual goal. So now here's where the science becomes really powerful. We anchor the lesson in a puzzling phenomenon. And this matters because science is fundamentally about explaining the world, right? The physical world. So instead of stating with vocabularies or starting with vocabularies or definitions, we start with something observable because that's what scientists do. All scientists, we're very good at making observations, right? Something that makes students ask, what did what did the phenomenon do? What just happened? How did it happen? And what's going on? And this is the big part. What data can we collect? What kind of observational or quantitative data we can collect? And cognitively, that's important because curiosity creates a reason to learn. The phenomenon gives students a problem space to investigate, not just information to memorize. This is part of why it's really important to focus on the phenomenon, the learning goals and the standards, right? As we create this foundation for the planning, what kind of thinking am I engaged in? And I would take some responses. Why introduce a puzzling phenomenon before direct explanation? What does that make possible cognitively for the students? Because what we're ultimately trying to do is get them to be aware of their own cognition and aware of what learning is for themselves, right? So that they can tie back to it later when they're engaged in everyday phenomenon and they want to turn something into science. Students have to have intellectual work when they're engaged in this thing. They're not receiving information from us. They're co-constructing it with us. They're trying to explain something, so we have to plan that. We have to plan how they explain something. And that shift matters because students learn science more deeply when they are engaged in sense making and not passive reception, right? So once students encounter the phenomenon, we begin eliciting their initial ideas. And this is where we surface students' prior knowledge, experiences, assumptions, and misconceptions. And from a teaching standpoint, this is incredibly important because students' thinking becomes visible. We explored this in session 3 and 4. And this might sound like, what do you know, what do you think happened? Or what evidence do you notice? Or what experiences connect to this? And what's powerful here is that students begin participating in science before formal instruction begins, and that changes the whole game. We're not front loading. We're collecting data as teachers in order to understand where kids are, what their misconceptions is, what their preconceptions are, and then building off of the accurate information, right? Let me pause again. When I'm engaging in that collecting of data, what do you think I'm doing? And why do you think I'm doing it? And most importantly, not only what am I doing and why am I doing it? Once I understand those two things, where am I going to go from there? Super important. Let's talk about it for a minute or two. Why might eliciting student ideas matter before we formally teach context? And based on student responses, what might the teacher need to do next? So once we have those conversations, I want to tell the teachers that this kind of information gathering is going to help us allow students to get comfortable describing phenomenon. And that's a major part of ambitious science teaching. That's a major part of developing the habits and mind of a science literate person. Not necessarily a scientist, but a science literate person, right? And then students can move into lesson activities. And the goal here is not simply activity completion. The goal is conceptual change. We want students engaging with evidence, models, simulations, and discussions, and data in ways that help refine or recognize, their thinking. And then also address those misconceptions. So students are not just doing science tasks, they're building explanations, and that's very important. And finally, we close the loop through evidence-based explanations. This is where students revisit their thinking and explain, what do I think now that's different than before? What evidence supports what I'm thinking? How has my thinking changed? And and that's basically the foundation to an argumentative epistemic practice, something that we teach kids to engage in, and then they engage in it all year long. That there's claim, evidence, and reasoning at work here, and that they're responsible for that, right? So if you step back and look at this whole model, what do you notice about the progression of thinking students are being asked to do over time? Exactly. What we really see is a coherent progression from standards to student sense making. And honestly, that coherence matters because rigorous science teaching is not just about covering content. It's about designing opportunities for students to investigate, reason, revise ideas, and make meaning over time. And as teachers, that means our job is not only to deliver instruction, it's to interpret student thinking, make instructional decisions, and create conditions where students can actively figure things out. So let's zoom in specifically on a puzzling phenomenon and get into the actual nuts and bolts of what that looks like in real time.